Yeah, thank you very much, everybody, for being here. I'm going to talk about PyForestScan, which is a Python library for large-scale LiDAR forest structural metrics. So it was built and designed to analyze forest structure using point clouds from airborne LiDAR data. So if you have like this airplane, it's doing this ALS scanning, you can then turn that data into plant area density profiles, like what we see on the right, for example. Why does it exist? It was really just to provide more tools for forest ecology and LiDAR in the Python ecosystem. I started this several years ago when I was a PhD student, and I was doing all my stuff in Python, and I didn't really want to keep switching between languages and environments, and I was kind of lazy, so I thought, oh, let's just stick with Python. It's easy, and my whole workflow was there. So, and it was really, at that time, I wanted to validate a lot of the JEDI-derived metrics. So a lot of the metrics that PyForestScan calculates are done kind of in a similar way and mirror what sort of the spaceborne LiDAR with JEDI provides. And there weren't so many open source software tools that tackled these problems and provide kind of easier solutions to calculate these metrics. So what are some of the things the library can do? It can classify ground and create digital terrain models. It's just kind of the starting point for a lot of things. It can sort of calculate point densities across different grid cell sizes. It can calculate canopy height and build canopy height models. It can calculate fractional canopy cover and do canopy cover rasters. Can calculate plant area density across different sort of vertical bins or slices. Can calculate plant area index, which is very analogous to leaf area index, which is a very, very useful metric in ecology and when looking at forests. It can calculate foliage-height diversity, which tells you a little bit about the complexity of the forest and the sort of the complexity in the vertical structure in forests. It has some tools to help visualize these metrics. It can work across very large landscapes. So like the big island of Hawaii, which is pretty big. And then I'm sort of integrating now tools to investigate points across flight scenes or like scans and swaths, and to get a little bit more into like the details of the point cloud to like try to understand why there might be artifacts in the data. And do all this in a Python environment. So I'm working on another project where I'm using, trying to segment individual trees and classify tree species, and then I'm using PyForestScan to give that information about forest structure and feed that into that puzzle. And so how does it do this? Well, it first voxelizes the LiDAR point cloud, so it sort of splits everything into these 3D grid cells, and it will count the returns in the vertical layers to track the points that are going in and points that are going out. And then it sort of estimates the gap probabilities in each of those height bins. So that's done using sort of Beer-Lambert law, and that will help derive forest structure. There's a great paper by Kamosk et al. In 2019 that describes this. They built an R package, which is fantastic, and it uses the same sort of physics. And from that, it computes the core metrics, such as plant area density, which, if you take this gap probability, which is, the number of points, that's SE, they're coming in, or sorry, ST, which is the number of points coming in, all the points that go into that voxel, SC, the number that are emitted through, get that fraction, apply it to the Beer-Lambert equation, which is that little one on the bottom here. L is like, for instance, the amount of plant matter that's blocking the attenuation of light, which is what Beer-Lambert describes. So solve for that, which is PAD. You get this equation, plug that into, that's how get your Python code to do that. And then you have plant area density, and from there, all the other metrics kind of follow. Well, not all of them, but a lot of them follow. But you don't need to worry about that. This is why PyForestScan exists. It will do that for you. And you can create maps of forest structures. So this is in the big island of Hawaii, Pu'uwa'awa'a, which is a cinder cone. So should also be nice to see this elevation as well. Should have made that map. This is canopy height model on the right in sort of 1 meter resolution, and on the left, foliage height diversity. And yeah, so how can you use PyForestScan? Well, to install it, there are 3 core dependencies. Python is the maybe most necessary. Well, they're all necessary, and PDAL and GeoTIFF, and this PyForestScan certainly wouldn't exist without these libraries. PDAL especially, a lot of the heavy I/O and stuff really it relies on PDAL. So big shout out to those guys. And to install it, it's on PyPy, so it's pip install PyForestScan. To install the whole thing, with your GDAL and PDAL dependencies, you can use Conda. It's probably the easiest way. So Conda, create your Conda environment, Conda forage channel. I'm going to include Python 3.12. PyForestScan is supported on versions 3.11 and up. And PDAL and GDAL, activate your environment, pip install PyForestScan. PyForestScan is not on Conda yet, and then it's there. And then to use it, this is a little bit terrible because it's just a line of text. A screen of code, but whatever. So, for example, if you want to calculate plant area index, you would import the modules and functions that you need. So from the handlers module, you'll import the read LiDAR function, and it supports LAS, LAS, COPC, EPT. I work a lot with these very big data sets, and working with the EPT file format is pretty sweet. So that exists. There's some visualized functions like the plot metric function where you can plot whichever metric you're calculating. There's some filters which kind of leverage the PDAL filters, so you have to filter height above ground or ground points or whatever. And then the calculate functions, so the function to assign the points into those voxels to calculate plant area density, and it's hidden behind the screenshot of plant area index, but the calculate PAI function. So you set the file path, read LiDAR, read that file, give it this coordinate reference system. There's an argument HAG, which is height above ground. So you can calculate height above ground from if you have a classified LiDAR. There's also functions to classify your LiDAR point cloud, classify ground. If you have a classified LiDAR, like LAS file, it'll calculate height above ground using methods that you can ask it for, or you can also supply a DTM, and it can read it off that DTM. You wouldn't have height above ground as a variable typically. It's not a LAS standard, but you might. So that's the read LiDAR function, and then that filter height above ground, I guess, is not really necessary. It's just this is a screenshot from some documentation. Get the points from that point cloud. Define the sort of the grid size that you want to analyze the data in. So your voxel resolution and XYZ. Assign the points to those voxels, so you know which points are in which bin, and then you can calculate the metrics and visualize them. So this is actually not 5 meter by 5 meter. This is a 30 meter snapshot or screenshot of plant area index along, where is this? In Laupahoehoe Forest Reserve in northeast part of Hawaii Island, if anyone's been there. So documentation exists. It's at, where is that? It's at that QR code, pyforestscan.cefa.ai. There's some binder notebooks and stuff that exist. I think right now when you go to those binder notebooks, it's going to say, oh, the Jupyter notebook file doesn't exist, but then you can still, like, the one that does exist is there, so I need to make that update. But there's should be pretty, I hope, some comprehensive enough documentation. And yeah, what does it look like when we apply it to data? So if we want to map forest structural metrics on Hawaii at varying scales, for example, this is what I'm doing right now. Canopy height models, canopy cover, plant area index, foliage height diversity across various scales, so upwards from 1 meter, 1 meter, 10 meter, 30 meter, and 250 meter resolution products. And I apologize, I meant to count, and it's right there. It's just like, EPT summary of your point cloud. I don't remember how many points are in the entire data set, but it's across 3 different years. The 2018 has 63 billion points, so it's over 100 billion points for the whole point cloud. With a point density of 8 points per meter squared. And I sort of have I have that and the bare earth DEM, so I'm just using that DEM to calculate that height above ground when I'm loading the point cloud and calculating these metrics. And the processing steps that I take to do this is I download the data. I guess there are no download data functions yet in the library, but that's not a hard one to do. Do some pre-processing in PyForestScan, so removing outliers. We can also do this in PDAL or whatever toolchain you want. This is a single SPL LiDAR system, and there's some issues with some of the overlap across scans, and so this is right now actually outside of PyForestScan, but I have a little PDAL plugin library extension to help try to equalize some of those points along these overlapping areas, because right now there's these terrible stripes that exist. But then use PyForestScan to calculate height above ground, build the EPT with Entwine, and then compute the metrics in parallel, tile-wise, across the whole landscape, calculating CHM, PAI, FHD, and canopy cover, and then merge those tiles at 1 meter resolution. It takes just a few hours, which is, I guess, long, but it's not that long. So it's a lot of points. And then this is some of the output that you can see. Sorry, I don't have too many visuals. But yeah, you have, those gaps are gaps in the data. It wasn't wall-to-wall coverage of the entire island. But yeah, for example, plant area index across different points. That's area in Hamakua Coast at Lapahoihoi, Puvava'a, South Kona. And I'm a little bit early, but maybe hopefully there's a lot of questions, or maybe it's right on time. This is the GitHub repo. Would love any, to work with more people. It's not so many contributors at the moment, but there are some, and special thanks to Ben Lehman, Ryan Peroi, Kaoru Kitajima, and other contributors. Yeah, thank you for listening.
Thank you very much. Super interesting. Long time. You have to talk about something there. Any questions from the audience? Yeah.
Hey.
So for above 30 meter, is it possible that you could alternatively use Sentinel GRD or SLC data for better visualization and after processing?
So sorry, can you repeat the question is, can we use Sentinel or other tools or data sets to?
Yeah, since in this specifically above ground mass, when we measure, it is the results have been a little bit better as compared to the LiDAR data.
Have they? So the question is, have they been better? Are they better than what you'd get? So if you're calculating something like leaf area index from optical data, it's using a whole different way of calculating the metrics differently. So this is using forest structure, and these metrics are really geared towards forest structure, and it's purely from the LiDAR. Okay. So yeah, I haven't spent so much time actually with some of the optical
And
data sets.
one more question. Regarding the GCPs that you used in the LiDAR data, is it specifically only from LiDAR, or there is like ground truth points also?
So it's a great question. The question's about GCPs, ground control points, in the data acquisition. So for the data that I showcased here, I had no hand involved at all in the data acquisition. So this is published by USGS and NOAA, and hopefully they did all the quality assurance and checks and stuff that they were supposed to do. PyForestScan itself doesn't offer any of that sort of functionality. Thank you.
Hi. Are you able to recognize on all the single tree and make like a boundary around the tree? Because I saw a picture that it looks something like.
Yeah, this one.
Yeah.
So segmentation in the point cloud is not something that exists in PyForestScan yet.
Right.
It's something that I think would be very cool to bring in. I
have a piece of code that is doing that. It's not the efficiency, so you have to improve it.
Yeah.
But it's online somewhere. I can look
Yes.
for that. Is it looking? Huh?
Yeah, no, there are several methods, and I'd love to talk more.
Now I have to leave, but we can catch around.
Okay.
No, I have a presentation in another room, but for lunch we can speak about it.
Okay, yeah, thank you.
I'll have a question before you leave.
Yeah, one thing I was thinking of was to at least have a wrapper for the segment any tree, which is the C++ one I was looking at, but I'd love to talk about yours. Sorry.
While you're talking about that, I can also send you some papers about exactly that. One of our students wrote probably segment anything as well. But the question I have is, what level of classification do you need from the LiDAR data to be able to do all this? Do you need vegetation classification, or can you do it from non-classified points?
At this point, you do need ground classified points. There are some functions to help classify ground. Yeah. But you need it depends actually, sorry. Because you need to calculate this height above ground dimension, that's kind of the core one. And from that, to do that, you can either have a ground classified point cloud, or you can import a DTM as well and use that. So, depends.
Okay.
Thanks.
If I can have a question, and maybe you have not tested for robustness for that, but if you have a dense, tall forest and you have structures inside the forest, does that influence the outcomes of your indices, the computation, or do you have some way of distinguishing that something is tree and something is not tree?
Not tree, yeah, like you have some buildings in there or something. At this point, no. So that would be something that you would kind of pre-filter before you brought it in. So because it's not working with like classified point clouds besides the ground, if you had a really nice classified point cloud, and you could filter out anything that's not, so you could use PDAL for this, filter out anything that's not 5 or 4, or if it's last specified.
Well, I guess the question is how to classify that, because
yeah.
of good ways. Yeah.
No, that would be, that's also a great thing to have in the library.
Sorry, can we pass the microphone?
Hey, I was just wondering if you could talk to temporal sequences. We have 2 LiDAR surveys over time. How comparable are these indices? And say if the LiDAR surveys are at different point densities?
If the LiDAR point clouds are at very different, what, sorry?
Sorry, if they're at different point densities, say we have LiDAR surveys 1 year apart, maybe
Yeah.
they're using a different sensor. Can we use these indices to make comparisons?
I mean, They are sensitive to the vertical structure of points. That's how these metrics are calculated. And so long as that sort of distribution is comparable, yes, but you'd have to, I think, be pretty familiar with the data and, kind of know if you have if you have a sensor in year A and then 3 years later you get this amazing one that's a lot of penetration, then it wouldn't probably be the best comparison. Yeah. So
Thank you.
Yeah.
Okay, thank you for your presentation. In our countries, we can obtain the radar point data as open data, but they just include X, Y, Z point, so that we don't have some kind of return numbers or a number of returns.
Right.
So it's terrible. So I have a question. It is possible to using the PyForest without such kind of properties?
It actually is. However, it won't read like there are only certain file formats that are supported, like a PCD point or PC, like from the point cloud library. That's not something that I'm supporting right now. So you would use something like PDAL or some other tool to convert that data set. It only needs to be XYZ, but into a file format that's ingestible by PyForestScan, which at this point are LAS, LAS, COPC, EPT.
Okay, thank you very much.
No, thank you. Good.
We will pause it there for questions. And I think Joseph will come back at the end of the session.
Yeah, I have to go to another talk right now, sadly, but I will be back for the third one and then here afterwards.
We just developed a thing for measuring the volume of trees. So.
Yeah, cool. Well, that's something that I need. Thank you. That's something, yeah. Okay.